We present neural congealing, aligning images to a joint semantic atlas. In this work, we address the task of joint visual alignment. Given a set of in-the-wild images that are semantically related, our goal is to detect and align the most common content across the set, in this case, butterflies. This is done through a test-time training approach where we jointly learn dense mappings for each one of the images in a self-supervised manner, resulting in dense correspondences. The learned mappings can then be used for editing the image set with minimal effort. By visualizing the average image of the transformed images, we can apply an edit and automatically propagate it back to the original images. We take inspiration from the tremendous progress in representation learning and leverage a pre-trained DINO-ViT model, which its features have been shown to serve as an effective visual descriptor, capturing localized and semantic information. Given the set of images, we aim to learn a joint 2D atlas that represents the common mode of DINO-ViT features across the images, specifically the keys. Each semantic part of the object across the sets is to be warped to the same location in the learned atlas. To that end, our method learns to jointly align the images in the DINO-ViT feature space, learning both the mappings and the joint atlas simultaneously. In practice, we use a spatial transformer network for learning the transformations. Most related to our work, Congealing proposed a GAN-supervised method for densely aligning an entire domain. Their method jointly learns a mapping network and a target mode across a large collection of images. This is done by leveraging a pre-trained StyleGAN to generate images as well as use its style pose disentanglement as training supervision. They got impressive results on complex data. However, they require a StyleGAN pre-trained on the domain of images which we want to align, and require additional training for learning their mappings and common mode. Also, they are restricted to the target mode that was learned across a large collection of images. On the other hand, we propose a test-time optimization framework which works on small in-the-wild image sets. Our framework is trained end-to-end in a self-supervised manner and learns the common mode that matches the given image set. In more detail, given a set of images, we use a pre-trained and fixed DINO-ViT model to extract the image's keys from the deepest layer. The mapping network predicts dense mappings for each image, which are used to transform the DINO keys to the joint space. Then, we apply keys loss to match between the transformed keys and the joint atlas keys. In addition, to detect and focus only on the common content, we optimize for a saliency value in each atlas pixel. To that end, we extract initial saliency masks using the method proposed by Amar et al. And apply a voting-based saliency loss between the transformed masks and the atlas saliency. This allows us to robustly align only the common regions, even in highly cluttered scenes. We also apply additional regularization losses to improve convergence. Please see our paper for more details. During training, our method jointly learns both the mapping network and the atlas representation. Here we show a few sample results. We have the given input set, the initial saliency masks extracted in pre-processing, and the final result of the aligned images. We can further visualize the average image in the joint space, together with a PCA visualization of the atlas keys, which emphasizes the different semantic parts of the object, and finally, the atlas saliency. Note the set contains large variations in appearance, structure, and pose of the common object, as well as cluttered background or other distracting objects, which are also present in the initial masks. Our method is able to capture the most common content while ignoring the background clutter and detects the best orientation and transformations for obtaining dense alignment. It also allows minor distortions for aligning objects that have different shapes and proportions between semantic parts, like the neck of the animals. Our method also works on sets containing images across different domains, such as paintings, statues, crochet dolls, or real animals, that all share a similar representation in the DINO-ViT space, which also applies to images across different classes. Once we have learned the mappings in the joint atlas, we can use the average image across the set in the joint space as template for editing. Then we use the learned mappings to automatically propagate the edit back to the original images. The edits are mapped correctly to the same semantic regions in all images. We can also extend it to work on videos, where we choose a subset of representative frames for training. Then, at inference, we pass all frames and apply the edit as before. Our method relies on semantic similarity in the DINO-ViT feature space. Therefore, it relies on these features to capture the semantic association across the image set. In cases of extreme topological changes in the common object across the set, our method struggles to converge to a good alignment due to strong rigidity constraints. We also notice that in sets containing symmetric objects with large rotation differences, the relative position between parts may affect the convergence and may lead to partial alignment. In general, our framework is not designed to align images depicting more than one instance of the shared mode. In this case, our method may align arbitrarily one of the objects or may fail to converge. Thank you for watching. Please check out our webpage for more details, results, and code.